Okay, dear students, today let me discuss about the atomic spectra. Okay, it's the one of the very important topic in our chemistry we should learn and we should try to understand. So from your different teacher or when you go through the book, so you can learn some idea about the atomic spectra, or from your different teachers you may get a different idea. So let me share my idea and my observation about the atomic spectra. I think you can may feel very easier to understand. Now here is spectra. So the term spectra, when we started learning, so I think it's not a much difficult to understand. Okay, now here in a very easy way how we can explain about the spectra. So you please just think like that. Okay, spectra are a series of radiation, no? Series of radiation. Now here the question is, what do you mean by radiation? Okay, in our previous classes we explained about the radiation. No, so here radiations, okay, are the form of the energy. So there are two different form of the energy. We learn, okay, that energy are associated with the particles. So either in the the particles moving at the velocity, or the particles moving down, okay, in the form of the wave, that are called mass particle and wave particle here. So that different form of the energy, one is the Einstein energy. So that is the E is equal to mc square, right? The second one is the Planck energy, okay? So that is E is equal to h nu, right? So these two different form of the energy we learned at the time of the electromagnetic radiation here. So that idea also we can coordinate with our atomic spectra. Here let we start to know about the atomic spectra. So before I start atomic spectra, so let we try to realize the structure of the atoms. So I think we know at lower classes we learn how to draw the structure of the atoms. Now see here I draw the very simple model of our atomic structure. So at the center of the the atoms, we have the nucleus. So around the nucleus, okay, so different imaginary circular parts are there. So this circular parts, what we call, I think you know it, orbit, right? So starting from the nearest to the nucleus, that I just numbering here, 1, 2, 3, 4 and 5, right, and so on. So the number of the orbits can be increased right here. Though now here let we just think about the energies. Okay, so in our orbits, okay, the definite quantity of energy associated with it, so that energy we call the energy level. Energy levels, right? Okay, so that means the quantity of energy associated with the first orbit, second orbit and third orbit, four orbits, so on, right? That quantity of energy at different orbits are different, right? So nearer to our nucleus, okay, the energy associated with the lower, the first orbit is the lowest energy level, and when the number of the orbit increase, the quantity of energy associated with them also increases, understand? So that means higher the number of the orbit, that is the highest energy level, okay? So this circular part, this circular the energy levels we can draw in the form of the line. Just I draw in the form of the line. Just in a very simple way, we can just draw like this. Okay. So from the nearer to the nucleus, I start numbering. That is the 1, 2, 3, 4, 5, 6, so on. Right. Okay. Here, our electrons which are present in different orbits. Okay. So here the very interesting phenomenon takes place. Very interesting one here. That's the key interesting phenomenon is that so electron can be jumped from the high energy level to the lower energy level, or from the lower energy level to the higher energy level. Such types of the phenomena we call the excitation of electron. So, or you can say the transition of electron. So there are two different phenomena. Okay, so excitation of electron, it means the jumping of electron. Jumping of electron. So I write it jumping. Jumping of electrons. So that is jumping of electron from one energy level to another energy level, right? So here, so the energy levels, it may be from the higher energy level to the lower energy level, or from the lower energy level to the higher energy levels, right? So on the excitation of the electron or transition of the electrons, okay, so series of radiations, so it may be absorbed from the some source of the light, okay, or it may be emitted from the excitation of the electron. That means we have two different types of the atomic spectra we can consider here. So what are the two different types of the atomic spectra? Number one is then number two is so here there are two types of the atomic spectra we can consider here. So due to the different types of the different phenomenon of the excitation of the electrons in our atoms here. So number one type is the absorption spectra, and the second one is the emission spectra, right? So how absorption spectra are formed? Here I show you. So absorption spectra are formed by the excitation of the electron. That means from the excitation of the electron, so here the how the electrons are excited from, so here from lower energy level to the higher energy levels. So by the excitation of the electron from the lower energy level to the higher energy levels, right? So the series of the radiations are so absorbed from the source of the light. That types of the spectra we call the absorption spectra. So I just show you the simple diagram here. See, this was the our energy levels of our atoms, right? See here, this is the lowest energy level 1 and 2, 3, 4, 5, 6 and so on, right? So one of the electrons here, I just write one of the electron from the lowest energy level. So it can be from the 1, or it can be 2, it can be 3 to the higher energy level. So let's we discuss this the electron which is the present at the lowest energy level here. So this electron, it's just jump up to the n is equal to 1. That means I just write n is equal to 1, that electron is jump to the n is equal to 2, right? So this is the lowest energy level and this is the higher energy level. When this electron from the lower energy level to the higher energy level, so some quantity of energy is required, right? That amount of the energies are absorbed from the our source of the light, right? That is the form of the radiation it's come out, right? So that energy I just write here, Planck energy. So this is the energy absorbed for the excitation of the electron from the n is equal to 1 to n is equal to 2. That's I write here. So I write the first, this one is the first excitation of the electrons, right? Then another excitation just I can write here. This electron can also jump up to the n is equal to 3, right? So the another form of the energy, that means form of the radiation which are absorbing. So another form of the energy absorbing here, that also just equivalent to the H nu. So I write here n is equal to 1, it goes to the n is equal to 3. So that is the second excitation of the electron, right? Then another one just I can draw here. This is the third excitation of the electron. So for this excitation of the electron, so another form of the energy absorbing here, that is I show you here, right? So similarly that also n is equal to 1 to the n is equal to that is the 4, right? So that I write here n is 3 H nu. Similarly it can be write like this, it can be write like this. So here the our radiations, like this. This is the energy which is absorbed from our source of the light, okay? So this is the another radiation, so that I write here. So I just mentioned 1, 2, 3, 4, 5. These are the energies which absorbed by the excitation of the electrons in the form of the energy in the form of the series of radiation. Here some of the radiation reaching faster, some of the radiations come slower and come slower, right? So all these energy are not same because the excitation of the electrons are different, right? In different excitation of the electrons, so the quantity of the energy absorbs also different. That quantity of the energy are absorbed in the form of the radiation. That radiation, so it's come, some of the radiation come fast sooner, some of the radiations come later. So that radiation just come as a series of the radiation. That is what we call a spectra. This is called a spectra, right? So now just these radiations come faster, slower and slower, slower and slower. So series of the radiations are developing in different excitation of our electron from the lower energy level to the higher energy level. That type of the series of radiation what we call absorption spectra, right? So that is next. The second type of the spectra, what shall we call? Emission spectra. So emission spectra is just opposite of our absorption spectra. Here also the excitation. So I write emission spectra. How emission spectra are formed, that is also the excitation of electrons. So from the higher energy level to the lower energy level. So I write from where? From higher energy levels to the lower energy levels. So now here, see, I just saw the same diagram, okay, which I drew in the case of our absorption spectra. Now here n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, or here it can be n is equal to 6. Now the difference from our absorption spectra, okay, from our emission spectra, it is, so in our emission spectra, the excitation of the electron, that means electron jump from the higher energy level to the lower energy level. Suppose let me choose here the lowest energy level. Here is n is equal to 2. Now here, so electron from the higher, so the higher energy levels of the n is equal to 1 is 2, 3, 4, 5, 6. All these are the higher energy level of our n is equal to 1. So one of the electron is just jumping from the, okay, just from the n is equal to, see, one of the electron. So that electron is jumped from the n is equal to 6 to n is equal to 1. Just I write here n is equal to 6 to n is equal to 1, right? Now here is the highest energy level. So this energy level and this energy level is different. Now this is the higher energy level, this is the lower energy level. Just let me take a simple example that how much energy, suppose 6. How much energy here is the 1. So when the 6 comes to the 1, so 5 is more than 1. So that much, okay, amount of the energy is, okay, emitted here in the form of the radiation, right? So that radiation, okay, so I just write in the form of the energy, that is h, okay, nu. So let me say here, okay, I write a 6. So that is the excitation from the that energy higher level, that is the n is equal to 6 to the n is equal to 1. So here that is the 6. Now again from the energy level 5, so another excitation also takes place from the n is equal to 5 to n is equal to 1. So I write n is equal to 5 to n is equal to 1. So that energy also, okay, just emitted in the form of the radiation, that is the E5, that is I write as nu. So another excitation we can just draw like this, n is equal to, E, okay, n is equal to 4 to n is equal to 1. So what the form of the radiations that is released like this, okay. So here that is the radiation can be released. Similarly, n is equal to 3 also can be released in the form of the radiation, and that is the another form of the radiation for the excitation of the n is equal to 3 to n is equal to 1 and n is equal to 2 to n is equal to 1, right? So here this series of radiations are, okay, so different, that means different energy. So different excitation of the electrons, okay, are different in the energies here. So that means different energy means different form of the radiation. Understand? So that form of the radiation, it's move in different speeds, right? In different velocity. Some radiations some radiations get traveling faster. Some radiations travel slower. So that radiation just move the series of radiation, okay, such a series of radiation, that also what we called spectra. So that is spectra, how these spectra are formed for the excitation of the electron from the higher energy level towards the to the lower energy level. So that type of the spectra called emission spectra. That means the radiations are emitted, not absorption from the sources, right? So that means these spectra are emitted from the excitation of the electron itself. So that is what we call as, okay, emission spectra. Now here, our interest is emission spectra, okay. Now here in our excitation of our electrons, so from the higher energy level to the lower energy level, so I write the excitation of the electron. So excitation of the electron from the higher energy level to the lower energy level. So what are the higher energy levels? So let me start it from the n is equal to from the higher. So I start from the 6, 5, 4 as we write before 3. So now 2. So from that higher energy level, the electrons jumping to the lower energy level, that is equal to 1. So as we mentioned, that series of the different form of the radiations are emitted in the form of the series of radiation, right? That is what we call a spectra. So here we found a series of the radiation. So we have the one type of the spectrum, right? Another series of the radiation can be right here. So it started from the higher energy level. So the lower energy levels now I just here 2. But in the first cases, the lowest energy level is the 1. Now in the second cases, right, I think I write in the second cases, the lowest energy level here is 2. So in that excitation, the spectra are formed. Okay, so the spectra formed in this excitation, the spectra formed in this excitation of the electrons will be different because the lowest energy levels are different. Then number 3 case we can consider here from the higher energy level. So I started from the 6, 5, 4, the lowest energy levels. So I just write a 3. Then next we can write n is equal to, I started from the 7, 6. So here I just write 5. The lowest energy level is a 4. Then I can start from the higher energy level. So I write 8. 7, 6. Now I just write here the Kn is equal to 5. So we have a different lowest energy level. In different lowest energy levels, so series of the radiations are formed. That series of radiation, what I call the spectra, should be different since the lowest energy levels are different. Understand? So because of the different inner lowest energy levels, so what are the different types of the series formed? So I write the different types of the spectrum series here. Number 1, so that is what we call Lyman series. When the lowest energy level is n is equal to 1, that is the name of the series, what is called Lyman series, right? And when the lowest energy level is the 2, what is the name of the spectrum series? That is the Balmer series. Don't forget, right? And when the lowest energy level is n is equal to 3, from the higher energy level, that is what we call the name of the series, Paschen series. Okay. Then the fourth one, so that is what we call Brackett series, and the fifth one, that is also Paschen series, right? So these are our different types of the series which are found in different excitation of the electron in different lowest energy levels here. Now here, so what should we remember? That these higher energy levels, it can be choose any one of them, but so for a particular series, so the lowest energy level should be remain unchanged here. Say for example, let me say here n is equal to 5. I just do it. The lowest energy level n is equal to 1. So here is the excitation of the electron from the n is equal to 5 to n is equal to 1. What is the name of the series? That is the Lyman series. Or it can be choose this one, 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 but only the thing is that lowest energy level n is equal to 1. That type of the series we can say that Lyman series. Similarly here also, right? So for the Balmer series, the lowest energy level it should be 2. The higher energy level, it can be choose any one of them. So it can also start from the 8 also, it can be say any one of the higher energy level to the lowest energy level. So we can choose that if the lowest energy level is 2, the name of the series should be the Balmer series. Same case the remaining are also. Now here, these are the form of the radiation here. As we know our radiations, we have the non-radiations. So I just remind you, gamma ray, X-ray, UV, visible IR, radio wave, microwave, so many types of our electromagnetic radiation. So these electromagnetic radiations are different in their frequency or in their wavelength, right? So for the our radiation, so we have the range of their frequency, they have the range of their wavelength. See, I mean that. So for the X-rays or for the UV, so they have the range of the frequency. It might be started from this much and this much, and UV also this much to this much, and the visible, as you know, the 7 different colors of the light, so that are called, that is what we call a BQ, right? So we have a different range of the frequency. So in our IR also we have the range of the frequency here, that are non-radiation. Okay, so when we calculate the radiation, what is the wavelength, what is the wavelength of this, what is the frequency of that, when we do calculate that frequency, what we found it is corresponds to our wavelength for non-radiation here. So after we calculation, so the radiation in our Lyman series, the frequency, the wavelength from the Lyman series, from the Balmer series, from the Paschen series, from the Brackett series, the frequency ranges are corresponding to our non-radiations here. After we found that, so Lyman series, the frequency the frequency of the Lyman series Kr corresponds to our UV light, right? And similarly Balmer series, so the frequency corresponds to visible light, and the Paschen, Brackett and Tiffins, they are all ranges of the IR. So but here in the Paschen series, that's the IR is the near IR, and this is the middle one, this is the far IR. So these are our range of the frequency of the particular series of our spectrum. Now, so please don't forget in your examination or in your competitive examination, so these types of this series is the very common question for you for different excitation of the electron, and these are our non-frequency which are corresponds to our particular series. So I think it should be remembered here, right? Now beside that, so what should we understand that, so in your competitive examination it may put up questions like that, by giving the one of the excitation of the electron. Suppose I just give you the one of the simple example here. This is the excitation of the electron. Let me write here n is equal to 4. It can be here n is equal to 2. So it may be asking you what is the types of this series. They may give you the number of the options there, right? They may give the number of the options like Lyman series, Balmer series, and Paschen series or Tiffin series, right? By giving these different four series, so we have to choose that for this excitation which of the following series correspond, which of the following series belonging. So just you look the what is the lowest energy level, right? See here, this lowest energy level is n is equal to 4, that n is equal to 4, that is for the Balmer series. And by giving these types of any one of the series, they may asking you just giving these types of the option here, A, B, C or D, something like that, right? Now here, so by giving these options, so they may asking you the Balmer series which of the following frequency is belonging, right? Or this which of the following frequency is corresponds to the Balmer series. So if for Balmer series it should be the visible. If they ask the Lyman series, it should be the UV. or for the Paschen series it should be near higher. So these are the common question. And one more here. See, I think you still remember that this, okay, non-electromagnetic radiation, okay, which one is the highest frequency, which one is the, okay, lowest frequency, or which one is the shorter wavelength and which one is the longer wavelength. So I think you may remember from the electromagnetic radiation. So but I remind you again here. So as I just mentioned once again here, gamma ray, then X-ray. So that is the order which can easily remember that: visible, IR, right? These are our known radiations, are very common radiations. So comparing their frequency, so gamma ray is the highest frequency, then the X-ray, then the UV, then the visible, and then the IR, right? And now, so what the relation between the frequency and the lambda? So we know that frequency is the reciprocal of the lambda. That means shorter the wavelength, greater the number of the frequency. That means greater the frequency, that will be the shorter wavelength. Longer the wavelength, it should be the lesser. That means, so when I draw like this is the, okay, the part, okay, I mean this is the wave nature where our particles moving in the direction of propagation here. So in 1 second, suppose I mark it here 1 second, this is the 1 second. Just in 1 second, right, how many numbers of the waves travel, right? That is what we call a frequency here, right? So now the distance between the two consecutive waves, that is what we call wavelength. So this number of the waves, I mean, okay, very maximum number of the waves in 1 second, that means highest frequency. Why this frequency is very high? Because the wavelength is very short. Suppose I just draw the same time and time period, so the wavelength is just, I draw like this, right? So look at here, comparing this, the distance between these two waves, right? So this is the first wave, this is second wave. See, comparing to that one, so the wavelength is very longer here, the wavelength is very short here. Same time period, in the same time period, the number of the waves traveling here is the very less, because the wavelength distance very longer. So here the wavelength is very short, and since the wavelength is short, number of the waves are very high in 1 second, right? So that means from the relation we confirm that, okay, the wave frequency is the reciprocal to the hour, wavelength c is the velocity of light, no doubt is constant, right? Now here, in opposite to the disorder, right? So gamma ray is the highest frequency, so this gamma ray should be the very short wavelength, and IR compared to the other, it should be the longer wavelength, right? So now here from this concept we confirm that, so IR is the longer wavelength, then the visible, then the UV. So by choosing these types of the, okay, radiation, these types of the frequency of our known radiation, so which one will be the longer, which one will be the shorter wavelength. So by giving the different types of the series, so they may ask you, okay, so which of the following series, okay, having the longest wavelength, so it can be asking to you, or shorter wavelength, it can be asking to you, right? So please remember that as per the calculation, you know, so the radiation, okay, as we know, related to their wave, so the characters, what we know, the frequency, the character, what we know, the remember that about the wave, that is the wavelength. So how do we calculate our, okay, frequency or wavelength of our particular series of the radiation here? So the very simple calculation, we should remember that one of the very important equation, that is called Ribot equation. This equation, okay, we using to calculate our frequency or wavelength of our, okay, series of the spectrum, okay, which are formed in different excitation of the electron. Here, what are the equation? That equation only to calculate the wave number. So wave number, so we have the equation R is divided by 1 by n lower, I should write n lower square minus 1 by n higher, okay, square. So n higher means the higher energy levels where the electron is jumping, and this is the n lower means lower energy level, okay, the electrons jumped up to that, right? So now if you know the lower energy level, if you know the higher energy level, suppose I just write n is equal to 4 to n is equal to 2. So this n is equal to 4 is the higher, n is equal to 2 is the lower. So we can calculate the wave number, that is the R is divided, okay, is into n lower is the 2 square minus 1 by 4 square. Then we can calculate easily by doing the simple calculation. This R is value, this is what we call constant. This constant we call the Riebeck equation constant. So this constant value will be given to you. I think approximately this R is value is equal to 1017, I think 977, something like that, right? That is per centimeters. Okay. So this value will be given to you. By putting this value, we can calculate the wave number. Now here, what is the wave number? Okay. So this formula you please remember. Okay, sometimes we can calculate in your theoretical exam. Okay. And how do we calculate? It's very simple. Now here, what is the wave number? Here wave number is the number of the wave. Just number of the wave. Okay, in 1 meter. So when our just determine the number of the waves, I suppose this is the 1 meter, right? So I can draw the very short wavelength, just we can draw like this, right? Or we can draw the longer wavelength like this, right? See here, so how many number of the waves are traveling in 1 meter, right? Okay, that's number of the waves, that is what we call wave number, right? So here, so I draw the two different waves, right? One is the short wavelength, another is the longer wavelength, right? Longer wavelength, so the number of the wave is very less. Shorter the wavelength, so the number of the waves is the maximum in the same distances, right? That means what is the relation between the wave number and the wavelength? So I confirm that wave number is the reciprocal of the wavelength. That means longer the wavelength, okay, lesser the number of the wave, that means it's opposite, right? That means shorter the wavelength, that means maximum number of the waves traveled in the particular distance. That is what we call a wave number. So when we calculate the wave number from our above the Riebeck equation, after we calculate, we can calculate the wavelength. If we can calculate the wavelength, so we can calculate the frequency also, because C the lambda, right? Now here, if you know the lambda, so we can calculate the frequency. If you know the frequency, so how do we calculate the wave number? So wave number is that means 1 by lambda, so I can put it here, C by lambda. So here wave number, frequency is the C into 1 by lambda is the wave number. So that is the formula we can calculate, right? So by that way, so we can calculate what are the different frequency wavelength of the different series of the radiation in different types of the atomic spectrum, right? So you please remember, these are the idea which I can share about the atomic spectra, right? Okay, so you please try to understand and just go through it, and so once you understand, so you can see the what the relevant questions in your previous exam, or what are our key questions related to our competitive examinations. So if you interest, so you just can send a comment also, you can ask the question also. Okay, it's just I give it a free of your okay any mind, so you can share with me. Okay, don't forget.